Now in 1D box, I think we have done a lot of that postulate, those things, everything. Okay, we have learned lot of things. So that's why in harmonic oscillator, apart from this method, solving, finding eigenstate, eigenvalue, again, I don't think we need much more, what you call, basic ideas. Okay, basic parts are almost done. Only thing is we need to take care of it. Okay, yeah, linear harmonic oscillator. Let me call it as LHO. Okay, which is one of the important problem in whole physics actually, because it has a lot of applications. Okay, not only in one or two domain, it has application in many domains. Okay, if you take condensed matter physics, if you take atomic and molecular physics, like that. Okay, and again, and this modeling, this quantum mechanical modeling of harmonic oscillator, that has got application in field theory, actually field quantization. Okay, so that's why this problem is very, very important for us. Okay. Now again, we shall see classical harmonic oscillator. Then we shall go to quantum harmonic oscillator and we can compare the idea, isn't it? In case of classical harmonic oscillator, let me, the best example is your a mass which is attached to a spring moving on a frictionless surface. Am I right? So spring constant K here. So this is its equilibrium position, x equal to 0. Is that okay? And it's a frictionless surface. It can oscillate. Is that okay? Now look at here again. What is your Newton's second law says? F is equal to minus K into x. Am I right? Or F is equal to m into d square x by dt square. That's what Newton's second law says. And that force is given by minus K into x. Am I right? This is a Hooke's law. Hooke's law in one dimension, isn't it? So that's equal to minus K into x, and you can solve your differential equation. Am I right? D square x by dt square plus omega square x is equal to 0, where omega is defined as, speak out, system property. Isn't it? Omega is a system property, not any particular of motion. Am I right? We have seen that kind of idea. So then we have solved this what you call differential equation, A cos omega t plus B sin omega t, isn't it? So then I have taken some initial condition that at t equal to 0, x of 0 is equal to A. I mean it is at one of the extreme position. Let me take like this, or x of x naught. Let me take x naught or A, whatever. Okay. So I mean I'm just dragging this one, root of k by m. I'm just dragging this one by a distance A. Okay. And then I'm just leaving this one. Okay. Or I'll call it as x naught. X naught. Okay. So x of 0 is equal to x naught. And again, I'm just leaving this one with a 0 initial speed. That means dx by dt at t equal to 0. That's also is equal to 0. Is that okay? Zero. So now look at here. If you substitute this one, your x of t will be equal to x naught into cos omega t. You can just check that out. We have done this one. Okay. Where x naught we call it as amplitude of the motion, isn't it? Amplitude of the motion. Shall I write A? I feel comfortable with A, amplitude. A looks like amplitude, isn't it? Is that okay? Now again, actually these two, you better put these two different then. Okay. C1, C2. Is that okay? That's not the same A. This was a constant came in the solution of differential equation. Later we found that constant. That constant found to be A. Are you getting my point? Yeah. Now find the velocity. What is the velocity? Minus A omega sin omega t. Okay. A omega sin omega t. So that's nothing but V actually. Now, how do you find energy? Energy of the particle system. Okay. Half m v square plus half kx square. Am I right? half mv square, half kx square. I better write k in terms of m and omega, because in quantum mechanics also we don't talk about k, we talk about omega. Okay, characteristic frequency, isn't it? So that's equal to m omega square x square. Let me write like this. Now substitute v, substitute x here, v and x here. So just check out what would happen. Okay, so that's equal to half m v square a square omega square sin square omega t plus half m omega square a square cos square omega t. A square cos square omega t. When you take those things common, you will get half m omega square a square sin square omega t plus cos square omega t 1. It will be independent of time. Total energy is conserved. That's what we say. Am I right? And observe this one. What happens? What you call in case of classical case? Okay. Classically, look at here, energy can be any value. Energy can be 0 also. You can keep particle at rest. You can keep this mass at rest classically. You can put 0 amplitude. You can make it to have any possible what you call amplitude. You can have continuous range of energy. Am I right? A can be any value here. But quantum mechanical, that is not the case. We shall see. We can't place the particle at rest. We can't keep the what you call harmonic oscillator system with 0 energy. Okay, we shall see that one. And we can't have whatever the energy we want. Okay, once omega and mass that we decide, okay, it is fixed. So again, energy is decided by the nature. Energy levels are decided by the nature. I hope you know that one. Am I right? Quantum mechanically, what would happen? N plus half h bar omega, where n is equal to 0, 1, 2 and so on, isn't it? We shall solve that one later. It's a quantum mechanical energy, classical energy. Okay? Classically, you can have continuous energy. Classically, you can have mass at rest. Quantum mechanical, look at here. If you put n equal to 0, you get half h bar omega. Okay? Yes. Lowest possible energy is not 0. So, these are the differences that you need to observe here. Okay? Now, along with this one, just check out this. How do you write potential for this one? So that F is equal to minus dou V by dou X, isn't it? That's equal to half kx square or half m omega square x square, because we need potential to find Hamiltonian. Am I right? We need Hamiltonian for quantum system to solve the Schrodinger equation, isn't it? Now we shall see this potential curve here. Okay. Half m omega square x square. Assume that it is symmetric almost. Okay. Is that okay? Now, classically, you can have any energy. What again? Our habit is, look at here. We draw potential curve, then we discuss about energy. Is that okay? Now look at it. Suppose if you have energy E here, it's a symmetric curve. Am I right? So what are these 2 points? Look symmetric.
No.
Not bad. Isn't it? So if this is A, this will be minus A. Isn't it? I mean, this is x equal to 0. This is your mean position. 0. Again, when x equal to 0, your force is also 0, isn't it? So this is the extreme position. Am I right? At extreme position, energy is equal to potential energy. Now, how do you find this energy quickly? Isn't it? How do you find this energy quickly without doing this one? At extreme position, your energy is equal to potential energy. Am I right? If you put x equal to here, you will get energy. At extreme position, E is equal to V of x. Can I write like this? Potential, this is V of x, okay?
Yes.
Potential energy at x equal to A, that's nothing but total energy. You can quickly get that one. Is that okay? Yeah. Now particle is going to oscillate here, isn't it? So particle is going to oscillate, and we have seen the probability density. Am I right? These are the, let me list out all classical answer. Am I right? What is the probability of finding the particle? Something into 1 by root of a square minus x square. Am I right? Particle is more likely to be found at the extreme position, isn't it? Again, if you draw this one, rho of x as a function of x, actually particle cannot go outside this minus a to plus a classically, isn't it? We have seen this probability density curve. It is like this. Do you remember first chapter? Make it symmetric, isn't it? This curve, this is some normalization factor, isn't it? Particle cannot go outside, only you have probability density which is varying like this, isn't it? Now look at here, you have more probability of finding the particle in the extreme position. Your probability density is maximum, that is minimum at mean position, okay? In quantum mechanically, in ground state, exactly reverse will happen, you will see, okay? Gaussian function, okay? And one more thing is, quantum mechanically, particle can exist outside this region of, look at here, we call this region as classically allowed region. This region, we call this classically forbidden region. Particle cannot go here with this energy E, isn't it? So classically forbidden region. So can I say like this? Classically allowed region. Why? Suppose if you go to this region, at this region, look at here, your potential energy is higher than your energy, isn't it? So what is the kinetic energy of the particle? Half mv square is equal to E minus V of x. So if you go beyond this region, your potential energy will be higher than the energy, your kinetic energy would be negative. That will never happen, isn't it? So that's why once you give this energy, so by dragging the your mass to one of the extreme position, it will start oscillating. It will be bound here, okay? Bound motion. We say bound motion classically. So surprisingly, what will happen is quantum mechanically we get non-zero probability of finding the particle outside this region. You will see that one. Is it okay? Classically forbidden region, because if a particle exists in that region, kinetic energy would be negative, because in that region your potential energy is more than your energy, okay? This is the energy level. This axis is energy, okay? Is that okay? So we call this region as classically allowed region. Outside that region, we call that as classically forbidden region. And this is our classical probability density for classical linear harmonic oscillator. These are the classical ideas, am I right, that we can list out.
When we drag the spring to the extreme position, it will store the potential at the...
Yeah. Again, when you drag and leave here, that means you have given this much potential energy. Now when you leave, force will be non-zero when you leave it here. That force will drag it to here, okay? And then you have inertia here. You have kinetic energy, which is maximum. You have inertia. Because of inertia, it will continue its motion to other extreme position. And again, you have force, which is so towards mean position. Like that, it will continue. If there is no friction, again, amplitude will remain same, isn't it? Undamped oscillation. Yes.
So sir, in classical harmonic oscillators, there is no discrete energy.
No discrete energy. Look at it. You can give any amount of amplitude here. You can make it zero amplitude. I mean, no oscillation at all. You can make it at rest. But if you put it at rest, remember its position and momentum are well known. Position is x equal to 0, momentum is 0. It's well known. And classically, we know position and momentum, isn't it? This is multiply with mass, you will find P, isn't it? Everything is well known here. You can say at this time, you will have this position, this momentum. Are you getting my point? Classically. You have x of t, you have v of t or p of t if you multiply by mass, isn't it? So that's why classically you have well-defined position and momentum, okay, which are variable, and you have energy which is continuous. You have probability density which is zero outside. I mean, there is no what you call probability of finding the particle outside. Quantum mechanically everything will change. You can't have what you call position and momentum information. Okay, energy will be discrete. You will not have any control over it. You can't say that I will change the amplitude. Is that okay? Because we are applying that one to microscopic system, and very important part is again this particle. There will be non-zero probability of finding the particle outside this classically allowed region. We shall see that one. This is whatever the potential we write here. Okay, whatever the potential we write, this is very idealistic. Is that okay? This is very ideal potential. Ideal means it will not happen in lab. I mean, bookkeeping. Half kx square, half kx
Not
square.
very
Half kx square. What do you mean by this one? Whatever the amplitude of oscillation you give, it will do oscillation. Am I right? But that will not happen. If you drag it too much, spring will what you call not. That Hooke's law will fail. Am I right? Hooke's law will have some what you call limit, isn't it? If you drag the spring too long, what will happen is it will not come to its what you call original position actually. Is that okay? This F is equal to minus kx or V of x is equal to half kx square. There is a limit for this one. Okay, you can't have x between minus infinity to plus infinity.
Sir,
Hmm.
sir, when I differentiate x is equal to minus del by del x,
Hmm.
then integration will be kx square. One constant will become right potential.
No. What we say is force is derived from the potential. You can put some constant here, but force will be again when you take the derivative, you will get minus kx only.
So I was thinking that
Potential always have got built-in ambiguity. If you add any constant to potential, force remains same. Force is a physical quantity.
okay, force is okay, but
Hmm.
when the constant will be sensed,
Again, what we do is look at here. This constant we again later in quantum mechanics, this constant will come in energy actually. If any constant comes in the potential.
So in the classically, we know that when the potential will sense, the
Hmm.
origin will shift to the another position.
Yeah, so wait a second. I think I can argue this one. Okay, this constant have got no physical meaning. You can always shift your origin so that you can make that constant zero. Origin is our choice, isn't it?
Yes, sir.
You can shift the origin so that you can make this constant zero. Let me argue that. That's the best idea. Now look at here. It will not happen in practice. Am I right? For any displacement, this will not be potential. This Hooke's law will not hold, isn't it? If you drag it to too large distance, Hooke's law will fail, isn't it? So that's why in practice, no potential will be perfectly harmonic. We call this one as harmonic potential. Okay, perfectly harmonic. Our potential curve shape may be quite different. Is that okay? Let me take one generalized potential. Look at here. Suppose I have a potential. Again, it need not to have what you call have minima at origin. Okay, I have some potential. Okay, I have some potential. So which has a minima at x naught. Is that okay? I have some potential which has a minima at x naught. Okay, I'll make it quite smooth here. Is that okay?
Any
Some arbitrary function. I mean, again, it may go like this. Okay, some arbitrary function. Or let me take it like this only. Is that okay? Some arbitrary function, but it has a minima. Minima means what? Look at here. If you keep particle here, okay, in this kind of potential, it will not move at all. That means you are not giving any energy, am I right? Minima of the potential means it's a stable equilibrium. We call this one a stable equilibrium. X naught is a stable equilibrium. So because if you keep particle here, again its energy may be like this again. If you keep particle here, it will not move at all. Is that okay? What will happen if you displace the particle? If you displace this particle, particle will try to come to this equilibrium. Isn't it? That's what happened in case of that spring motion also. Particle will try to come to that equilibrium position. Or if you keep the particle at that position, it will stay there for a long time. We call it a minima of potential energy curve. We call it a stable equilibrium. Okay, I call that point as x naught. Is that okay? X naught. So because in practice, look at here, we can choose origin anywhere. Am I right? That's why this need not be here always. Okay, that's why I have drawn the most general case. Is that okay? And how to apply our linear harmonic oscillator concept to that generalized potential? Now look at here. If you displace too much, it is not following parabolic shape, isn't it? It is not following f equal to minus kx actually. Are you getting a point? There is a limitation for Hooke's law. Yeah. Now look at here. Let me just this is v of x. Okay. This is not this v of x. Okay. Let me take new v of x. Let me just report this one because this will never happen in lab, isn't it? Now look at here. What I do is I am going to do Taylor expansion of this v of x about this minima. Taylor expansion about x naught minima, which is a minimum point. Minimum point of minimum. Okay. So how does Taylor expansion looks? You know that one? V of x naught, just go through that one. Plus plus V dash of x naught, derivative at that point into x minus x naught, plus V double dash of x naught, so x minus x naught whole square by 2 factorial, plus V triple dash, again first derivative at minima, okay, at x naught, second derivative at x naught, third derivative at x naught. I hope you know this one. So Taylor expansion, x minus x naught whole cube by 3 factorial and so on, isn't it? This is a Taylor expansion. Now what I do here is, look at here, I am going to restrict myself to small oscillation about this stable equilibrium. Okay, I am going to take small oscillation about x naught. That means, so again this deviation from this stable equilibrium is small. That means x minus x naught is very small. Let me take this situation. Is that okay? And observe carefully, what is this one? This is derivative at x naught. What do you mean by derivative? Derivative means slope of the tangent. What is the slope of the tangent at minima? 0. First derivative at minima 0, isn't it? X naught is a minimum point of minimum. Is that okay? This is 0. Observe this one. Okay. And one more assumption that I have taken here, small oscillation. I'm not deviating too much. I'm just restricting myself so that again this I'm just taking very neighborhood point here. My variable point, it is very close to x naught, so that x minus x naught is too small. So that what I do is I can neglect all higher order term. Don't neglect this one also. Look at here. This is already 0. Okay. This is a constant. If you neglect this one also, this will be constant. Keep some variable term. In any approximation, you should keep some variable term. Are you getting a point? So what do you do? Sine theta, you write sine theta nearly equal to theta. Am I right? What do you write? Cos theta you write nearly equal to 1 minus theta square by 2. Isn't it? You keep some variable part. You don't make it constant. Okay? In most of the case, we do like that. So that's why don't neglect this one also, but neglect all higher order term. Is that okay? Neglect all higher order term. Let me do it here itself. After making this approximation. And this is already 0. Pick out.
Sir,
Yes.
Sir, why we are taking a Taylor expansion about the minimum substitute? What is the physical interpretation behind it?
No, that's why I have shared one video by R. Shankar. Just check out what do you mean by Taylor expansion. If you have more and more number of terms, it can it can explain more and more region of this curve actually. If you have only some term, okay, some term, it can explain only some very minimum part of that one. Or maybe in the tomorrow session, let me show some graphs from GeoGebra. Is that okay? I'll make some graph out of Taylor expansion. I think you will understand it. Okay? Taylor expansion means if you have infinitely many terms, it will explain this whole curve from all region of x-axis. Okay? If you have only some term, it will explain only some portion of that one.
If we deal with our ideal situation, the parabolic curve, then I think there is no need to take the help of Taylor.
No. Again, if you take half kx square, if you take its Taylor expansion about x equal to 0, it is itself. Its Taylor expansion is itself. Think about, compare with Fourier expansion. Am I right? In Fourier expansion, if you had infinitely many terms, it would explain our curve very well, isn't it? If you have only some term, it will explain very roughly, isn't it? Like that. Here, Taylor expansion means if you are very close to this point about which you are doing Taylor expansion, it will explain only the region around that one. If you want to explain the whole curve, you should take more and more points. But here I have restricted myself to the point very near to this one. Okay, I'll come out with some plots from GeoGebra. Okay, just like I did last time for Fourier analysis. Okay, you will understand that one. Is that okay? Yeah. Now look at here. So when I restrict myself to very nearby point near to that stable equilibrium, so what will happen? I can neglect higher order term. I can just end it here. And this is already 0 because first derivative at minima, that means first derivative means slope of the tangent. So tangent is what you call horizontal over there, isn't it? Now I got v of x is equal to v of x naught plus half v double dash of x naught into x minus x naught the whole square. 1 by 2 factorial, let me write it as half. Okay. Now, what is this v double dash of x naught? You have to have some idea regarding this. What is the second derivative? V dash of x means dv by dx. Am I right? V double dash of x means d square v by dx square. Okay, at x naught. So this is slope. Am I right? This is slope. This is d by dx of slope. Am I right? Second derivative means derivative of slope, isn't it? That means what do you mean by derivative of slope? Look at here. Now that derivative of slope says how slope changes about this point. Derivative will always talk about how one variable will change with respect to other variable. Am I right? When I change x here, how fast slope changes? Whether slope is changing very fast or very slowly. That's what the second derivative says. The second derivative is a kind of physical quantity. Second derivative talks about curvature actually. If suppose curvature is more like this, okay, then what will happen? Slope is slowly changing. Slope of the tangent slowly changing, isn't it? If you take this kind of curve about this point, slope is suddenly changing. Is that okay? In this case, that second derivative is more because d slope by dx, which is more here. It is slope is changing very rapidly with respect to x. Slope is changing very slowly here. So that's why. So this second derivative at minima is small here. Second derivative at minima is large here, because slope is rapidly changing, slope is slowly changing here. So that's why this second derivative at minima will talk about curvature about minima. Whether curvature is more or curvature is less. This is less curvature, more curvature. Can I say like this? It's a kind of physical quantity actually. Now what I do here is that you need to observe, okay? You need to observe what is this one thing. And other one is what I do here is, so God hasn't decided this coordinate system. That was our choice, isn't it? What I do here is I'm going to move my coordinate from here to here. O here. I'm going to move this one to here. Coordinate origin to here. If I move that one here, look at here, this will become x-axis, new x-axis. Is that okay? Then what will happen if you move here? What is the minimum value of the potential? 0. You said some constant is added, isn't it? Now look at here, I am going to remove that constant. With respect to that new origin, I can make this one 0. Isn't it? So V O dash, this is V with respect to O, of x is equal to half V double dash of x naught, x minus x naught, the whole square. Now I am not going to stop. Look at here. I'm always free to choose the origin, isn't it? This is O dash. I'm going to move my origin from here to here. I'm going to move my origin from here to here. Is that okay? I'll call it as O double prime to the minima point. Okay? And with respect to this one, look at here. With respect to this one, your minima point x not equal to 0. With respect to this as the origin. So V with respect to O double prime of x is equal to, look at here, half V double dash of x naught is 0 here, x minus x naught, x square. This is nothing but very similar to half kx square. That okay? Now look at here, this V double dash of 0 is same as V double dash of x naught. Its value is not changing. Moving the origin is not changing the curvature shape, isn't it? I told this depends on second derivative at minima, that depends on curvature shape, isn't it?
I mean, when we observe the curvature,
with a different origin, it doesn't matter, isn't it? How slope changes about minima, that doesn't depend on from where you are seeing, am I right? I mean, what is your coordinate system? Where is your coordinate system? So that's why this is one very physical quantity. So that's nothing but our k actually. That will play the role of spring constant. Is that okay? And now, so today plot this one. Okay? Half x square, half 10x square, half 100x square. Plot that one. Okay? You will understand. That okay? Compare them. What is the role of this coefficient in case of parabola? Clear? So now the conclusion here is, look at here, when we move the origin to O double prime, look at the potential. Half kx square, which is constant into x square. Half kx square. Remember, what are the assumptions we have made? We are very near to this minima, okay? We are not deviating much from the stable equilibrium, okay? Now look at here. Look at the statement now. You are giving the oscillation now, but that oscillation is very small. You are giving the oscillation. You are studying dynamics only, okay? But that oscillation is very small. Can you write the statement? Any oscillatory motion is approximately simple harmonic. Simple harmonic means half kx square. This we call this as simple harmonic potential. Okay. Any oscillation about stable equilibrium. Any oscillation means potential can be any function, but it should have an equilibrium point, minimum point. Okay. Any oscillation about stable equilibrium is simple harmonic. As long as amplitude is very small. As long as amplitude is small.
So, Sanjay, once you can please explain why we ignoring high order terms.
No. Again, what I'm saying is, in practice, in lab, you will not have ideal parabolic potential. You will have some weird kind of shape. Am I right? There also you can have simple harmonic motion, but as long as amplitude is small.
So can you say that anharmonic oscillation?
Anharmonicity, again, this deviation from harmonicity, that we call it as anharmonicity. If you set very big oscillation, that may be anharmonic. That may not follow half kx square. That may not follow Hooke's law. But so set that small oscillation about minima. That will be simple harmonic. And for that we can apply all of our theory. Are you getting my point? So practically we will not have what you call pure parabolic curve, isn't it? In our potential, it will be anharmonic, as you said. It will not be exactly harmonic. Okay? So then what we do is, again, we are going to restrict ourselves to small oscillation about stable equilibrium. So then we can apply all of our theory. Because it will be half kx square in that sense, in that case. Is that okay? Just read out Griffiths now. Okay? Any oscillatory motion, okay, is approximately simple harmonic as long as amplitude is very small.
Sir, I was saying amplitude small means it tends to 0 or what?
If you make amplitude 0, particle is at rest, what is there to study? You are setting into oscillation, but you are making oscillation small so that you are in the regime of this parabolic region. If you zoom in this curve, if you just zoom in this curve, this part, you will see perfect parabola. That is the meaning of this Taylor expansion. If you just zoom in this curve, at that point, it will be perfectly parabola. Is that okay? It will follow half kx square nature nearby this one. If you set a big oscillation, it will not follow half kx square. If you set very small oscillation between these two, again, it will be simple harmonic. You can apply your theory for small oscillation. That's what I'm saying.
Then sir, for whole curve, we can, if we take small portion, then can we find
No. Again, particle will not oscillate about this point. If you just leave the particle, it will go here. Particle can oscillate only about equilibrium. Isn't it? Stable equilibrium. Particle can oscillate about equilibrium only. It will not oscillate about any other point. Okay? Just think over it. Suppose if you have a particle here, it will try to come to equilibrium. Again, so it will not come back to that point and it will not oscillate about that point, isn't it?
So is it possible that many more like this stable equilibrium point?
Yeah. Again, one potential curve, it may have more than one stable equilibrium curve. That can happen. We shall see many problems in classical mechanics. Okay? One potential curve, it may have more than one stable equilibrium point. Okay? It can have. Again, suppose here, so it may go here and it may have one more equilibrium. Okay? That can happen. Then about that point, you can have what you call your oscillation. That may have different curvature. That may have different k value. That will happen. Is that okay? Speak out. And we take this one as our potential. Quantum mechanical linear harmonic oscillator, half m omega square x square or half kx square. Again, we define Hamiltonian, that's equal to minus h bar square by 2m d square by dx square. So potential is time independent, am I right? Half kx square, isn't it? Minus h bar square by 2m d square psi by dx square plus half kx square, psi is equal to E into psi. Our aim is to solve this equation and finding psi and E. Okay? Because this is a governing rule in case of quantum mechanics, just like Newton's second law in case of classical physics, isn't it? You can put it as cap here, okay? It doesn't matter. Yeah. So tomorrow I'll proceed with this one, but before that, you better to read out these beginning pages of linear harmonic oscillator problem, and along with that, just work on this curvature, plot those curves, okay? Work on this Taylor expansion, okay? Let me give you some more idea regarding Taylor expansion, okay? Yes.
Whenever we take the space of any function, and the Taylor expansion stays, about what?
No, it is a other way of writing the function. Fourier expansion. What is Fourier expansion? It is other way of writing that function in terms of infinite series. Taylor expansion is also other way of writing the function in terms of x minus x naught whole square like. If you take infinitely many terms, then all of those terms together will represent your curve properly. If you take only some term, it will represent only the very nearby region actually. You will see that one. Are you getting my point? In Fourier expansion, it is not like Fourier expand about some point. It's a Fourier expansion about some region, isn't it? It's a Taylor expansion about a point actually. Okay, just watch that video by R. Shankar. I think you will get much more idea.
It's like Maclaurin series.
Maclaurin series, I think it is at origin it is called as Taylor series, I think. Am I right? No. Taylor series about origin is called as Maclaurin series, other name. Taylor series is more general. Taylor series, if you put x naught equal to 0, we call that as Maclaurin series. Other name. Is that okay? Am I right, anyone? Taylor series about origin is called as Maclaurin series, I think. Not any different thing. Okay? Speak out.
Analytical part is Maclaurin.
Analytical part. Now here we are talking about very well behaved function only, okay? Again, if you want to expand any function as a Taylor series, that should have derivatives, okay? Higher derivatives should exist. Are you getting my point? Can you hear me? Okay? You are taking first derivative, second derivative. If any function contains some sharp edge, just like we have taken earlier, like this, okay? Then you can't have second derivative at all, isn't it? First derivative will be discontinuous. You can't have Taylor expansion, okay? You can have Taylor expansion only when that function should possess some higher derivative, okay? Then only you can have Taylor expansion, okay? Curve should be smooth. Can I say like this? Smooth curves will have Taylor expansion. Can I say like this roughly?
Close to 0 in the Maclaurin series.
When you take Taylor expansion about 0, it's called as Maclaurin series. Taylor expansion is more general. That's what I'm saying. Okay? Not tends to 0. Taylor, yes, speak out.
There is symmetrical linear possibility.
Yeah, I mean, we made it symmetric by moving our origin to this point.
So what will happen if you make it asymmetric?
No, our wave function will change. Energy, those will not change. Wave function, probability density, our perception changes.
Sir, if we consider the whole graph, not any minimum or not any maximum, the whole graph is symmetry or asymmetry, right?
No, whatever, look at here, only wave function changes, energy will not change. Ultimately, any energy levels, transition, if you talk about in lab, those will never depend on your choice of origin. Is that okay? This wave function mod psi square, probability of position measurement, these are bookkeeping actually. Ultimately, our ultimate thing is energy level gap, transition, probability of finding the particle in respective energy, the lifetime of the states. These things have got application.
Atomic spectra and
Yeah, atomic spectra, I mean like that. That's what I'm saying. Is that okay? So that's why if you make it asymmetric, energy will not change. If you choose different origin, energy will not change. Energy is a very physical quantity. Wave function will obviously should change, isn't it? As we have seen from asymmetric box to symmetric box. Is that okay? That's why if we discuss symmetric potential, again, rest of all it will take care. Isn't it? If you shift the origin, you change the wave function. That's it. Okay?